Earth science time. Today we are talking about geologic time. Geologic time. It is both earth science time and it's geologic time is what we're talking about. And we're talking about, we're going to start by talking about two kind of concepts we need to know. Oops, am I even being recorded? Yes, okay. Two kind of concepts we need to know in order to even approach the science of Earth's history. And then we'll talk about what we know or what evidence there is for Earth's history. So the things that we need to talk about first are relative age dating. This is when you see a cute girl at your family reunion and you no, I'm just kidding. That is a pretty good joke though, because it's relative age dating. Shut up for a second. Okay, and then we need to talk about absolute age dating. This one there is no funny joke about, that's just the way it be. And the other one is fossils. And we're going to have a little box down here for fossils not because there's not a lot of cool stuff to talk about with fossils, but my goal is that by doing the scavenger hunt, you already know mostly about the things I would expect you to know about fossils. So we'll talk very briefly about them just so that it's recorded so you have something to go back to. But we're primarily going to focus on this. And these are going to be things that we've already talked about, and this is something we did a scavenger hunt on, so they're going to kind of fit in the cracks. For the relative age dating, I want you just to listen. I didn't mean that at all. I want you to list the 5 Steno's principles by Nicholas Steno. Remember those? 1, 2, 3, 4, 5. And then the kind of encompassing 6th one. Okay, we'll start with that one. Uniformitarianism. I'm going to describe it verbally. You don't need to write this down because you already have it somewhere in your notes. Good job writing it down, though. Uniformitarianism is the idea of what? I'm not going to write this. I'm just going to say it. And you're going to say it first.
It's like the same.
Okay, yeah, it's the same. The root word is form, which means shape. But uniform, meaning the same shape, this makes that adjective uniform into a noun, uniformitary. And then the ism means we're talking about the idea of the noun of the same shape. All of that's a little bit chaotic, but basically it means we assume that the stuff that is happening today on planet Earth was happening for all of Earth's history. So we assume that when we see, for instance, today, we see a river downcutting, a river cutting down into the ground at a rate of, I don't know, approximately a meter a year, we'll say, which is that's a large amount of downcut for a river. But let's say we observe that today. We can safely assume that a river in similar situations, even back in geologic time, would exhibit a similar rate of cutting. Basically, we don't make assumptions like, oh, this lake is here because a meteor struck. We don't just go ahead and assume that right away, because that's fairly uncommon. It would be a safer assumption to assume erosion or glacier. Similarly, we're beyond, or we like to think of ourselves as beyond the use of mythology for things like, oh, this volcano is here because the fire god was mad at us and caused all of our houses to burn down. We try to be beyond things like that. We assume that the same kind of stuff that happens today has been happening throughout Earth's history, or at least we attempt to use that as our main method of understanding. Now, does that mean that meteors never cause lakes? No, that can happen. Does that mean the fire god wasn't mad at you and burned your house down? That's not within the realm of science. I don't know. Maybe he was. But there's probably also a scientific explanation. Uniformitarianism. Okay, what are the other principles of Steno's principles? Superposition. Let's talk with that one first. Superposition, basically, just give me a real brief summary of all of these. Superposition. In a sentence or a sentence fragment.
Oldest to youngest stacked.
Yeah, oldest is on the bottom, youngest is on the top. Regarding what? Usually rocks. We're usually talking about rocks, but it's also true for fossils, although we wouldn't have a pile of fossils, but we might find fossils in the bottom layer of rock and then fossils in the top layer, and we could safely assume that the fossils in the bottom layer are older. We applied it also to sandwiches.
Yep.
Was it possible for me to overturn my sandwich and eat it such that the part that was on top was actually the first thing you laid down? Yeah, of course that's possible, but we call that overturning, and that's its own separate thing. In superposition, we say that in unoverturned sequences of rocks, the oldest are on the bottom. What's another one?
Horizontal.
Horizontal.
Original
horizontality, comma, original, because someone started me out wrong. Original horizontality means
It's gonna stay flat.
Well, it's like the original rock is
Yeah.
going out horizontal.
yeah, the original layer of rock was horizontal. So that means if we see a layer of rock that is like this, something else happened. In this case, probably what?
Tectonic.
Probably plate tectonics had something to do with it. But originally horizontal. That when they form, layers of rock are originally horizontal. What's another one? Cross-cutting relationships. Okay, tell me it.
It's like if something was to cut in between it.
Yeah, if any feature cuts across layers of rock, it must be older than those, it must be younger than those layers of rock. If we have the kind of classic examples, we have these layers of rock, and they have a fault going through them, and then we have a layer of rock that doesn't have that fault on top. We say that this is the oldest, this, then the fault is D, and then E and F, right? The fault is older than E and F because it's lower than them according to superposition, but it's younger than these ones because these, basically A, B, and C had to exist before D could cut across them, right? D couldn't cut across them if they weren't there. The slice in the sandwich must be more recent than the sandwich itself. Otherwise, what were you slicing? 4.
Lateral continuity.
Lateral continuity, Jinx. Lateral continuity. What does that mean?
If the first layer is like flat, it's gonna.
Yeah, lateral means referring to the sides. So if I see this, we'll say this is sandstone. It's the same kind of sandstone. Everything else is the same about them. What do I assume because of lateral continuity?
They used to be.
They were once like this, and then some other thing happened that made them like this. Probably erosion, maybe a fault. But that's lateral continuity. Okay? Inclusions. This one, Doritos. The Doritos in the sandwich, which is, I don't know if I like that a whole lot, but I understand how you probably would. But the Doritos had to exist before the sandwich could have Doritos in it. If the Doritos are included in the sandwich, they had to exist first. If this rock is made up of chunks of other rock, these chunks of other rock had to exist first in order to be included in that. Another one that I'll put as a star, it'll have to be kind of tiny because I ran out of room, is correlation. And it reminded me of that because of lateral continuity. But basically, if I find this layer of rock here, and 100 miles away, I find another layer of rock, even if it's below it. When I say below, I mean stratigraphically lower in elevation. If I find the same layer of rock in 2 different places, for instance, look out yonder window. Do you see the not the top part of the buttes, but the part of the buttes where it kind of starts to slope?
Yep.
That's the same exact composition and makeup of rock as the rock that is at the top of the monument, the Scottsbluff Monument. So it's the exact same kind of rock. So I find them a long ways away. What does that tell me? Well, I can correlate these 2 rock layers. Basically, if this one is found to be 35 million years old, which I'm not specifically talking about those rocks, I don't actually remember precisely how old they are, but if this one is 35 million years old, this one is too. That's called correlation. We can do that with fossils too. If I find this little fossil here, and I also find it here, we can say, and this one's, let's say, 55 million. This fossil is also 55 million. And therefore, this whole layer of rock is probably around 55 million years old. We kind of correlate it both in type of rock and especially with fossils. If we find this fossil here, and we know this fossil is 55 million years old, that tells us the rock around it is probably 55 million years old too. Questions about any of Steno's principles? Or these other guys? And that's how you date your relatives. Okay, absolute age dating. What does that refer to? So these ones are all,
Absolute age dating gives like exact dates.
yeah, actual, not exact necessarily, not exact meaning, a lot of people get confused about this. There's a question on the test that says, effectively, what is the difference between absolute and relative age dating? And a lot of times people put absolute age dating as more precise, but that's not it at all. They're fundamentally different things. This one is telling us relatively what are the ages of these things. How do they compare to each other? This one's all about comparison. Not, as this one would be, Kyler is 5'6". Is that true?
5'2".
Wow, I don't know what I'm doing. Kiera is 5'6", would be an absolute height. Kira is taller than Kyler is a relative height. In this one we're comparing, and in this one we're giving an actual value. So if we're talking about absolute age dating, we're talking about absolute age dating, we're talking about actual values, we're talking about numerical ages of rocks or fossils. And you don't have to pick one, right? This is not C's Dairy Sweet. We don't have to pick, do I want chocolate ice cream or ice cream?
C's Dairy Sweet.
I don't give a darn about what you're saying. We don't have to pick, do I want brickleberry or nutmeg? I don't know what the flavors of ice cream are besides vanilla because I only ever get vanilla. But we don't have to pick. We do both of them. Back to my drawing that I wish I hadn't erased. If I see fossil that I know or I can date somehow to 55 million years old here, and over here I see the same fossil, and I also have this sandstone layer on top, I use these two things together to say this layer must be,
45 million.
you're being too specific, it must be
Younger.
younger than 55 million years old. We use them together. So this one provides numerical ages, and these provide relative ages. They compare, and they're both useful in their own way, just like you all are useful in your own way. These are a lot more useful than you are. And how do we generally do this? There are a couple different ways. What's the main one that you're aware of?
They all have fancy names.
Radioisotopes is probably the most useful one for geologists. Radioisotopes. Basically, and someone did a lab about this about M&Ms. Basically, on average, radioactive elements, of which almost all the elements on the periodic table have some isotope that's radioactive. Some of the very common ones that we use are uranium. Uranium-235, I think, is the isotope specifically. We use zirconium. Where's she at? We use zirconium dating quite a lot. And there are others. Potassium dating. But we find a specific isotope, and we can measure how long it takes for half of that thing to go away. That's called the half-life. You remember this from physical science. Remember, what Greek letter was half-life? You remember? Ramrock.
Hanging upside down is light thingy.
Yeah, it was. You're right. That's not a Ramrock. Lambda. Lambda. So the lambda is the half-life, how long it takes for half of it to decay. And that's a known value. And it's an extremely safe assumption to make that when this rock crystallizes, and it has zirconium in it, for instance, some with zirconium isotope, that when it crystallizes, this is 100%, that isotope of zirconium is there present in 100%. And so then when we come back later and it's half zirconium and half whatever the daughter isotope is, which I don't know for zirconium, but it's half daughter isotope, we know that one half-life has passed since this rock was made, basically. Since this rock crystallized, one half-life of zirconium has passed. And so we say this rock is, I don't know what the half-life of that zirconium isotope is, I wish I'd done a little bit more research, but we could say this rock is, I don't know, 13 million years old. It'll be a miracle if that's the actual right number. Put it in the comments. But by doing that, we can see an actual age for the rock. Is that the only way? No, there are also things like tree rings and lake varves, which you can look up yourself. But this is the most usual and most common and most effective way that we use as geologists to date rock. The tree ring thing is really not super useful because trees don't live usually even thousands of years. And we're usually dealing with things on the order of millions or tens of millions or hundreds of millions of years in geology. Usually we're using this. But I'll put them over here. Tree rings. Is that who also does your yearbook?
Yes.
Tree rings, and we do, look up lake varves. And there are others. Varves, V-A-R-V-E-S. What about fossils?
Right there.
There he is. How do fossils form? What is a fossil?
It was one evidence of something that.
Okay, evidence of ancient life. Evidence of ancient life. Generally, we say to be considered a fossil, it must be greater than 10,000 years old. Generally. I'm sure there are exceptions. I'm not aware of any. What has to happen for this thing to become a fossil, this ancient life to become a fossil? It needs to be preserved. Is it always its body that is preserved? What kind of fossils are there? There are body fossils, and there are trace fossils. In the museum, they called those direct and indirect fossils. They also called the trace fossils ichnofossils. But basically, body fossils are evidence of what? You're right, morphology. Evidence of morphology. The actual shape of the critter, or plant, or worm, or whatever. And the trace fossils are evidence of, be more broad. Behavior. And you can see that in some cases, trace fossils are actually much more useful because we can't. Let's use uniformitarianism. What are the main ways we can learn about how these critters acted? Okay, yeah, if they died stuck together by their tusks, we know they've been fighting, right? That tells us their behavior. We know they were in must. We can infer later that they were in must. But can we tell a lot about how it behaved just by looking at its bones and stuff? To some extent. Like we can tell the Tyrannosaurus Rex or this little guy. Look at him. He's also on your bell work. I think this is supposed to be Archaeopteryx. But we can tell from looking at this thing that one of its behaviors was probably to fly. Probably flew. I don't actually know if that's true or not. We can tell that it walked on two legs. Look at him. Right? That's a behavior. I'm not trying to get gross, but we can probably tell from the reproductive structures whether it's sexually or asexually reproduced, right? Asexual things don't have genitalia, and so we can probably tell a lot about some of its behaviors by looking at its morphology, but not all of them. That's why when we find things like nests or fossils of their footprints or coprolites, you know what a coprolite is? Poop. Coprolites are fossilized poop, so we can tell about how it ate. Probably not very well. It did not have, it might have eaten better than you. It probably did not have 4 Red Bulls for lunch. It probably didn't have leftover spaghetti and 4 Red Bulls. Bye. Hey, can you, Lily?
It's mine.
Oh. Hey, can you read this? Okay, so if you know how to read this, like the MAPS test and the ACT, and you learned what I kind of went over with you, you can do a good job on this test, okay?
If not, I'm going to sue and then retest.
Well, I don't care.
Okay. Will you send me?
Bye, girl.
Bye. Please send chat to
We missed a couple things. Hopefully you learned from your book, too.